Hello everyone and welcome to a new problem from this chapter in which we are going to see how to apply the binary search in a special way. It might seem a little bit unusual at first, but trust me, you're going to be very impressed. So the problem is the factory, right? Let's read the statement. There are n workers in a factory. Each worker packs the same type of product, and for each of them we know the time it takes him or her to pack one product. We need to find out the minimum amount of time the workers need to pack at least k products, right? So we have this workers. For each of them, we know the time it takes to pack one product. For this example, we have 6 workers. The first worker needs 4 units of time. We can call them minutes, let's say, to pack a product. The second one 7, 3, and so on and so forth. And they need to pack at least 60 products. And the answer, as you can see, is 30. But let's find out why is that. Well, first of all, let's find out why 30 is even a good amount of time. So how do I know that those workers can actually pack 60 products in that time? First of all, you need to know, if you haven't understood the problem well, it happened to a lot of us, is that those workers pack the products independently, right? So they don't wait for each other or other stuff like that. So in 30 units of time, let's see how many products will the first worker pack. That is 30 divided by 4. And of course, because we can't pack like, I don't know, 1 product and a half or stuff like that, we have to deal with integers here. We are going to take the integer part of that, right? So we will have the integer part of 30 divided by 4, which is, of course, 7. So the first worker is able to pack 7 products in 30 units of time. Then the second one, 30 divided by 7. Integer part of that is, of course, 4. Then, third one, 30 divided by 3. Integer part of that is, of course, 10. 30 divided by 6. Integer part of that is 5. 30 divided by 7. Integer part of that is 4. And for the last worker, 30 divided by 1. Integer part of that is 30. So let's add these numbers together and see how many products all the workers were able to pack in 30 units of time. 7 plus 4, 11, plus 10, 21, plus 5, 26, plus 4, 30, plus 30. That's an exact total of 60, right? So it is pretty clear that if they have 30 units of time, they are able to pack 60 products, which is good. But if they had, let's say, 29 units of time, right? So for 29 units of time, what would have been the number of products they were able to pack? Well, 29 divided by 4 in integer part is still 7. 29 divided by 7 in integer part is still 4. 29 divided by 3 in integer part is not 10 anymore, is 9. Divided by 6 is not 5 anymore, it is 4. Divided by 7, still 4. And divided by 1 is 29, right? So it's pretty obvious that this sum is less than 60. So if in 29 units of time they weren't able to pack at least 60 products, and in 30 units of time they were able to do that, this means that 30 is the minimum amount of time they need in order to do the job. So now that we have just explained the example, let's, as usual, come up with a brute force approach for this. Alright, so how would you even come up with a brute force approach for this problem? Well, following our bulletproof structure to come up with brute force approaches, let's analyze again the problem. the problem asks us for the minimum amount of time in which the workers can pack at least K products. So from all the possible amounts of time, we are going to take into account only those that are valid, right? So that are big enough for the workers to be able to pack those products. And from all of them, we are going to take the minimum. So from one set of things, we need to take the minimum one as the answer. So let's try out each and every one of them, right? So one thing I can do is actually try out each and every amount of time, I'll just call it t here, ranging from, of course, I need at least 1 unit of time, all the way to, and what would be the upper bound? That's an interesting question. Always when thinking about upper bounds for the solution of problems, we need to obviously take into account the worst case scenario, right? And the worst case scenario here is having only one worker, which has to pack all the K products, and let's say it takes him the maximum amount of time possible to pack one product. So that would be K products, right? Crossed max time. This is like the, I don't know, the worst case upper bound. K crossed max time. So we can try out each amount of time from this range. And the second step of the brute force approach is just to see if that time is big enough. What does this mean? It means that we should see how many products all the workers can pack and check if the number of products is greater than or equal to K. So the second step is actually finding out how many products, right? So how many, let's say this is a function, right? How many products, all right, all the workers can pack in the given time t. This is our second stage, right? And of course, if how many products of t is, so let's write here, if how many products of t is greater than or equal to K, the first time that this happens, so for the first t that this happens, we have found our answer. So the minimum number, so the minimum amount of time they need is t, and we can just return t, right? And this is basically it. As simple as that. Just try out each possible amount of time, compute how many products the workers can pack in that specific amount of time, and for the first one that's greater than or equal to K, just return it. Now, the only question is how to actually compute this number of products, right? How many products of T? Well, we kind of answered that during the example, right? We have seen that for each and every worker, we need to add to the total number of products the integer part of T divided by the time it takes that specific worker to pack one product, right? So this is actually going to be the sum of every integer part of T divided by, let's say, time I, where I, of course, ranges from 0 all the way to the last worker n minus 1, right? So in order to compute this sum for each different t, we obviously need to make a for loop, right? We need a for loop which iterates through every worker and adds this value to our sum. So the brute force approach code is super simple. Let's take a look at it. All right, and here is our code for the brute force approach. As you can see, I am trying out each value of t, so each amount of time between 1 and k crossed the maximum time, which the maximum time could be like a constant. You can define it as a constant based on the restriction the problem tells us. Let's say if the problem tells us that the maximum time or the maximum value from the times array is something like 100,000, just define max time as 100,000, or you can even go further and compute it based on the array, find the maximum value, and that's it. That's not important. We are trying out each moment of time, right? So t equals 1, t equals 2, t equals 3. And for each value of t, we are going to see, is this value enough? And in order to check that, we will call the function number of products, which we have defined here. And if number of products of t, which means again, how many products all the workers will be able to pack in the amount of time t, is greater than or equal to k, then we just return t, right? So obviously, for some values of t, for example, maybe 1, 2, 3, and so on and so forth, the number of products will be less than k, because as the time increases, obviously our workers would be able to pack more and more like products, right? So at the first value of t, at the smallest one, right, for which this value is greater than or equal to k, we return t. And this is how we make sure that we will return the minimum amount of time, right? The answer of the problem. Now, as for the function, this is simple. We just have a variable number of products initially equal to 0. And for each worker, which has time, so for each time in the array of times, we are just increasing number of products by the integer part of t divided by time, because that's how many products that worker could pack alone. And in the end, we return the number of products. So for the time complexity, it is actually pretty simple. As you can see, the main algorithm is this one. So let's take a look here. And what's going to happen here is that, of course, this if statement, only the if statement alone and the return are constants, but I'm not going to write actually big O of 1 here because that's not a good idea. What I'm going to do is, this is constant, right? So this is pretty simple, but this line alone is not constant, and we're going to see why. So we have a for loop, which tries out each value of t from 1 to k crossed max time, right? And of course, it at some point stops when it finds the minimum value of t, which is valid. So obviously, it depends on the problem. It depends on the times array and k. The number of iterations of this for loop depends on that, right? Because if k is smaller or the times are smaller, of course, we are going to find a smaller t. But again, in the worst case scenario, we can go all the way to k crossed max time. So, because we don't have like a fixed number of the number of iterations the for loop does, we always take into account the worst case scenario. And the worst case scenario, as I said, is k crossed max time iterations, right? So k crossed max time. Now, let's see what are we doing for each of the t's. We are checking this if statement. And the beautiful thing here is that the if statement needs to call the number of products function. So the code inside the function obviously will be executed for each iteration in this for loop. For t equals 1, do all this above. For t equals 2, do all of this from here. T equals 3, and so on and so forth. So actually, we also need to see what is the time complexity of the function, how many iterations it does, because we are going to multiply the number of iterations happening here, of course, to the number of iterations happening in its parent for loop. So if we take a look at the function, this is of course constant, don't worry about it, constant, don't worry about it, an addition constant, don't worry about it. And we have this for loop which goes through each and every worker, right? So this is obviously n iterations as we have n workers. So the number of products function takes big O of n time complexity to be executed on each call. And how many calls do we have? We have one call for each different value of t, which are at most k cross max time. So the final time complexity of the algorithm is big O of k crossed max time. So k crossed max time and crossed n. This is the time complexity of our brute force approach. Now, As any other brute force approach, obviously, don't worry about the time complexity. Let's see how we can improve that. And as we have learned, in order to do that, we should separate the stages of the brute force approach, right? So what the brute force approach consists of is, first, it tries out each and every t in this range. So trying out each and every possible time until we find, of course, the first one that's valid. And the second stage of the brute force approach is actually computing for that value of t how many products will be packed. So let's say number of products, right? From the function's name. These are the two steps, right? Obviously, the first step does k crossed max time iterations, and the second one does n iterations, right? So in order for the final time complexity, which is the product of those two, to be optimized, we have to think about which one of them can actually get optimized, can get way smaller, right? Now, the number of products can't be optimized, unfortunately, because for each different value of t, the changes are not like from, I don't know, maybe from time t to time t plus 1, you can see that there are only a couple of changes or stuff like that. We can't come up with a formula on how t evolves, on how number of products of t evolves over time. So we need for each value of t to go again and go through each and every worker and compute the sum and return it. For the next value, compute again the sum and return it. So the number of products is actually good as it is for now. We can't optimize this process. But one thing we can do here is that we can optimize this one. This is not efficient, right? Going through k crossed max time different values of t is not efficient, and we can check a lot less values. Now, this is the interesting part, because you're probably wondering, Andy, how could you check only a couple of them? So if, let's say, k crossed max time was equal to 1000, how can you not check every time from 1 to 1000? Well, we need to search for the minimum time. And what we did here is apply a linear search. You can call it a linear search. Why is that? Because you are going through each value of t from 1 all the way to that upper bound linearly, and then checking if the value is valid. But there is also other technique which we have learned about earlier, which is called binary search. And yes, this is a super powerful thing the binary search can do, which is binary searching the answers for some problems. So not only binary searching elements in sorted arrays or binary searching, I don't know, any other stuff in some collection, you can also binary search some information that you are interested in. And obviously in our scenario, the information is the minimum valid t. We are going to binary search it. And let's see first why we can do that and then how it is done.